Hey, what's up? This is Anupam. Welcome back. This is the fourth tutorial on the video tutorial series on STM32F4 Discovery Board. You can check out my website www.logicvoltage.com. You can watch these tutorials at the website also. You can even check out the video store at the website. It has some good tutorial series there with a very attractive price. A lot of people are buying it. You can also get them and learn some very awesome things about embedded programming. And I'm sure you will not be disappointed if you buy them. You can get in touch with me also in case of any query. Just go to contact us page and fill up the form and I will reply. You can check out the forum also. For any tutorial related queries or any technical questions, you can just register yourself on the website and then create a new topic on the forum and write your questions and doubts, and I will reply back there so that other people can also see the comments and what discussion is going on. Please make some donations so that we can continue to create the tutorials free for you. You are welcome to choose any amount as you like for donation. We will be highly appreciated. You can also support us by giving a thumbs up at this YouTube video and subscribe my YouTube channel. Thanks. In the previous tutorial, we have learned about the libraries and how we used it in our LED program. Then we have changed the LED program to make the LED blink in every 1 second. To achieve that, we added a delay to make the LED blink, but make it exactly 1 second, we use the trial and test approach. Hence, in this tutorial, we will first learn what is meant by the frequency of the microcontroller, and then we will update the LED blinking program. Till now, we have written a complete program to make a LED switch on and then to make it blink. But there is one thing that still we didn't put our focus, that's frequency. Frequency is the speed at which a microcontroller executes instructions. Now, for example, if a microcontroller is executing 1000 instructions per second, then we say its frequency is 1000 Hz. Now let's take another example. Let's say we have two microcontrollers. First microcontroller executes 900 instructions per second and the second microcontroller executes 800 instructions per second. Then we can say that first microcontroller is faster than second. But one thing to keep in mind that two microcontrollers with the same frequency will not necessarily perform equally. Now every microcontroller has an internal clock in it, and that clock is continuously ticking. Now to execute an instruction, a fixed number of clock ticks are needed. This depends on architecture of microcontroller, that how many ticks are needed to execute a single instruction. Now in our STM32F4 Discovery board, we have STM32F407VG microcontroller. This microcontroller has an internal clock of 16 MHz that we can use. But in the STM32F4 Discovery board, we have a 8 MHz crystal oscillator. So we have two options to choose here. Either we can choose the internal 16 MHz clock to run our microcontroller, or we can use the external 8 MHz crystal. Well, in real world, generally external crystals are used. That's because they are more accurate. But in our STM32F4 Discovery board, we have one more options to choose. That's we call it PLL. PLL is actually not a clock. It uses the external 8 MHz crystal and converts it to any other frequency, which can be greater than 8 MHz. Now let me show you what are the clock configurations options we have available on our Discovery board. The first option we have is HSI, High Speed Internal. It's 16 MHz and this clock is internal in the microcontroller itself. The next option we have is HSE, that means High Speed External. It's the 8 megahertz crystal we have in the discovery board. Now we have system clock. It's the final clock which will be fed to the microcontroller. Or in other words, I can say that whatever the input frequency given on the system clock, our microcontroller on the discovery board will run on that frequency. Now we can give either this HSI to the system clock, so our microcontroller will work on 16 megahertz, or we can give HSC to system clock, so our microcontroller will work on 8 megahertz. Now we have one more option here, that is PLL. We have some PLL parameters here, that's PLL-M, PLL-N and PLL-P. Now we can give either HSI to PLL and then it will be sent to system clock, or we can give HSE to PLL and it will given to system clock. Now what's the benefit we are getting to pass through PLL? Well, if we pass through PLL, then we can change the frequency here by setting these PLL parameters. Let's say we have give HSC 8 megahertz to PLL, then set PLL-M 4, PLL-N 192, PLL-P 6. Then we will get 64 megahertz at system clock. Or if we set PLL-M 8, PLL-N 336, PLL-P 2, then we will get 168 megahertz. And similar kind of situation on HSI. If we give HSI to PLL and then set PLL-M 8, PLL-N 192, PLL-P 6, then we will get 64 megahertz at the system clock. So you can see that passing through PLL can change the frequency. We can get any higher frequency and run our microcontroller fast. Now this diagram is just a big picture of the clock configurations. Some other parameters exist also which I haven't shown here, which also affect the frequency. But the ultimate idea is similar to this. Now you must be wondering that we have already written a program that light up the LED and blink it. Then what clock source we are using on that program? We haven't defined anything related to clock selection in our program. So how our program is working, right? To answer that question, let's get back to our program. Now this is the program that we have written, and in this program we haven't mentioned anywhere about the clock settings. Actually, this clock settings is taken care of by the Atomic True Studio. When we create any new project, Atomic True Studio automatically set this for us so that we can directly start writing our code and we don't have to do anything for initial configurations. Now the clock setting saved by the Atomic True Studio is in another file called system.stm32f4xx.c. If you see the left side here, you will find system.stm32f4xx.c file in the source folder. Let's open this file. You can see that this file has lot of settings. This file is automatically created by the Atomic True Studio. We will go through the settings in this file in future tutorials, but for now our main focus is on clock settings. If we go down a little, then you can see this section. In this section we have lot of settings saved. Here the first line you can see that system clock source, that's PLL HSC. So this means that right now the clock source is PLL HSC. HSE means high speed external, as I already said. That means external 8 MHz crystal it is referring. Now, as I shown you before, that PLL is way of changing the frequency. So if you have 8 MHz crystal, then you can directly give the 8 MHz crystal to the microcontroller. Or you can use the PLL so that you can convert the 8 MHz to some other frequency. Here PLL option is used. So if you can see this second line, system clock 168 MHz. This line is telling that the microcontroller is running on 168 MHz. That means our PLL configurations is saved in such a way that the PLL is converting the 8 MHz external crystal to 168 MHz, and thus our microcontroller is running on 168 MHz. In other words, we can say that by default Atomic True Studio configure the clock source PLL HSC and clock speed to 168 MHz. That's the reason why we didn't have written any code for clock settings, because Atomic True Studio already have done this for us. Okay, now there is one problem here. If you go down a little bit and see this line, HSC frequency 25 MHz. This line is telling that our external crystal is 25 MHz. But in our STM32F4 discovery board, we have 8 MHz crystal and not 25 MHz. Actually, Atomic True Studio by default set these settings like we have 25 MHz external crystal. So here we have a problem. The problem is, although our program is still running, but our PLL configurations change the external 25 MHz frequency to 168 MHz. But in real, we have 8 MHz external. Hence, our microcontroller is actually not running on 168 MHz. It can be lower than that, and we are not sure what that is. Although for just switch on LED or blink it will work, as we didn't deal with any kind of real timings in our program. But future tutorials will be dependent on frequency of microcontroller. Hence, we need to solve this problem manually. So we will have to change some values here, as our external crystal is 8 MHz and not 25 MHz. If we go down a little bit, we can see this section, PLL parameters. In this we have 4 parameters, PLL M25, PLL N336, PLL P2 and PLL Q7. We will have to change the PLL M value. It's 25 right now, we have to change it to 8. Let's do that. Rest parameter values will have no change. Now we have changed the PLL parameter values as per 8 MHz crystal, as by default the Atomic True Studio is setting PLL values as per 25 MHz external crystal. Now there is one more place where we have to change on value. Let's go to the main program. If you go to the top part, then there is one header file we have included, that's stm32f4xx.h. Let's go to this file by holding the control key and left click on it. Okay, so now in this header file also we have many configuration values. That's by default set by Atomic True Studio when we created this project. We will look in many of these configurations in the later tutorials. For now, just go down a little bit and you will find this line. HSC value, that's 25 MHz. In this line, you can see that our HSC value is 25 MHz. This is wrong. HSC means high speed external and our external crystal is 8 MHz. Hence, we need to change this value also. Just replace 25 with 8. We are done now and we have now completely configured the clock settings properly. Let's run this program and see what will happen on the LED blinking speed on the board. Okay, first save all, then build project. Okay, so now build successful. Let's run this code on discovery board. Now you can see that our new updated code is running and our LED is blinking. Now when you run this code, you will find that your LED is blinking maybe a bit faster or slower than before. That's because our previous clock settings are not correct and our clock is running not in a speed of 168 MHz, which Atollic True Studio by default configured. But after we have updated some settings, and now our clock is correctly running at 168 MHz, hence change in LED blinking speed. Okay, so now we have learned how to properly configure clock settings. But you must be wondering that every time if I create a new project, do I have to change these clock settings before I can write any main code? Well, to be true, yes. Every time if you create a new project, just follow these steps and change PLL parameter and HSE value. Although it's not going to take much time, so just change it this way. Okay guys, so now we have properly configured the clock settings. So next thing we will do is change the blinking speed. We want the LED to blink at a delay of 1 second. Although after changing the clock settings, you will find that the LED is now blinking at nearly 1 second gap. Now if you have gone through with my previous tutorial, then you will remember that we have added these delay statements to hold the execution here. Hence our LED first switch on this line, then delay for some time, then LED switched off, then delay again, switched on, and these steps continue to go like this. To make this LED blink in 1 second, we have to make this delay of exactly 1 second. If you remember in the previous tutorial, I said that you can use the hit and trial method to make 1 second delay. Although that can be done, but that's not work always. If I say to make delay of 10 second or 500 millisecond or 100 millisecond, then it will be difficult and confusing. So to make this simple, we can do this in another simple way. We just have to do some calculations. Now let's see this delay function. In this delay function, we are actually passing a long integer value, and then this value is continuously decreasing one by one until it reaches 0, and then it returns to our main code and further executes. So actually our delay here is due to this processing to bring the integer value to 0 one by one. So right now we are passing 168,000,000 to the delay function. Hence our LED will first light on, then this delay function, and is called with 168,000,000 value. Then this delay function will continue to loop until 168,000,000 value becomes 0. After that it will return to our main code where it will switch off the LED on the next statement. Now our delay will be more if we pass big value, and our delay will be less if we pass smaller value. Now we need 1 second delay here. So we have to choose a number in such a way that decrementing that value one by one to 0 will take only 1 second. Not more, not less. So the question, how do you know if you pass any number and it will take this much time? How to calculate that? Well, there is a way to do that. Not exactly we can do, but still we can get an approximate number. Now we know that our microcontroller is now running at 168 MHz, and that means it is executing 168,000,000 instructions per second. So to get a delay of 1 second, we have to pass such a number in the delay function that exactly 168,000,000 instructions executes to bring that number to 0, and hence it will return from the delay function exactly 1 second delay is there. So in other words, I can say that we have to pass a number to the delay function that brings the number to 0 by decrementing one by one will take 168,000,000 instructions. Now make sure you don't get confused with instructions and statements. The program code we have written here line by line are statements, and instructions are different. You don't write instructions here. When you build the project, Atollic True Studio builds the instructions for each statement. Now a statement can lead to many instructions. For example, if you have written I++, then it is a single statement. But when it is converted to instructions, it can lead to more than one instruction. Instructions are actually hardware commands. Now hardware commands are actually a complete different topic, and that is beyond the scope of this tutorial. But one thing we have to find out is how many instructions we are executed when this delay function is executed. I have calculated that already, and it's 10 instructions per loop. That means if we pass number 10 in the delay function, then the loop will run for 10 times, and on each loop 10 instruction executes. So we have total 10 into 10, that means 100 instructions total. Hence if we get a 1 second delay, we have to give 168,000,000 instructions. So if you do a little bit of calculations, then you will understand that we have to pass 168,000,000 number, as on each loop 10 instructions executes, and thus total we will be having 168,000,000 total instructions in the delay function, and that is 1 second. Now let's again build this program and run it, and let's check if we are getting 1 second delay or not. Now our new program is running on this board. You can see that it looks like 1 second gap. Well, if you compare it closely with some other clock, then you will find that it's bit more than 1 second. That's because although in the delay function we have 10 instructions per loop, but there are some more instructions executes when the delay function is called. So those instructions are also taking time, and thus we are getting more than 1 second delay. But still this is much better than our previous trial and hit approach. Well, to get exactly 1 second delay, you have to learn about timers. In future tutorial we will learn timers. Timers can be used for accurate timing delays. For now, just keep it this way. Okay guys, in this tutorial we have learned about concepts of frequency or clock speed in microcontrollers. We have learned how we can update the clock settings in our project, and then we have updated the LED blinking program to blink in exactly 1 second. In the next tutorial we will move on from this discovery board to a breadboard. We will use external breadboard and work with some LEDs and create some cool lightning with LEDs. Once again, this is Anupam from logicvoltage.com, and thanks for watching. Bye.